Hello Math 8 students, this is Open Up Resources Unit 1 Lesson 7, No Bending or Stretching. To get started we have this little warm-up. We have these different segments of some rulers. Some have some really large tick marks, some have some really smaller tick marks separating it up into smaller pieces. What I want you to do is find the length of each line segment to the nearest whatever it says. So for the first one, the length to the nearest 1/8 of a unit. The length to the nearest 0.1 of a unit, you have to understand what that means. And again, the length to the nearest 1/8 of a unit. So pause the recording, put down your estimates, and then we'll continue with that information. Okay, so as we're finding the length of these segments, this is to the nearest 1/8 of a unit. So we can see that each one of these inches is broken up into 1, 2, 3, 4, 5, 6, 7, 8 pieces. So each one of these smaller tick marks represents 1/8 of a unit. So I can see that this is a full 1, 2, 3, 4, and then measuring to the nearest 1/8, I'm going to be counting. This is 1, 2, 3, 4, and 5 eighths. So I would call this 4 and 5/8 of a unit. This segment says to the nearest 0.1. What does that 0.1 mean? Well, 0.1, if I say this correctly, is 1 in the tenths place, so 1/10. And when I write 1/10 as a fraction, it tells me, and it makes a little bit more sense, what I'm actually seeing. That means that these are broken up into 10 pieces. And let's take a look. Between the 1 and the 2, 1, 2, 3, 4, 5, that's our halfway mark, 6, 7, 8, 9, 10. So to the nearest 1/10 of unit is going to be to that nearest tick mark. Let's take a look. I have 1, 2, 3, 4. We can see 1, 2, 3, 4, 5, 6, 7 of those little tick marks. So this is measured 4 and 7/10. And now let's take a look at the last one. We're going to estimate the length of this segment to the nearest 1/8 of a unit, which means it is now no longer marked, but I still need to follow that process. That means I'm going to break up this section into 8 pieces, just like it was up here. I can see if I were to go straight down the middle there, that would be halfway through. So from this section to this section, I'm going to break that up into 4. 1, 2, 3, 4, and I'm going to break that up into 4 more. 5, 6, 7, and 8. So it looks like it is approximately 3 and 1, 2, 3, 4, 5, 6. So 3 and 6/8 of a unit. Now 6/8 of a unit does simplify. So even though it's to the nearest 1/8 of a unit, 6/8 does simplify to be 3/4. And now let's repeat or finish up this last one. Looks like we're repeating this estimate, this time to the nearest 1/10 of a unit. So this time when I break it up, I'm going to go ahead and get rid of those. 0.1, remember, is that 1/10. So now I'm going to break that up into 10 pieces. Here's that halfway mark again. This time I'm going to break it up into 1, 2, 3, 4, no, too much. Let's see. 1, 2, 3, 4, 5. Break this up into 5 more pieces. 1, 2, 3, 4, and 5. So to that nearest 1/10 of a unit, there's 1, 2, 3, 4, 5. Remember, that's my halfway. 6, 7. Not quite to the 8. So I would say 3 and 7/10 of a unit is my estimate there. Interesting. This 3 and 3/4 ends up being 3 and 0.75, 0.75. This is 3.7. So you can see when I'm measuring to or estimating to these different amounts, you can see that they're not going to be precise. That was a little bit different than this because we're breaking it up into different pieces. Okay, moving on from the warm-up. What we're going to be doing now is we're going to be practicing some transformations. It says translate polygon A, so point P goes to point Q. That means this point is going to move all the way over here to Q. When we're doing translations like this, we can represent that translation with a vector. I just drew that vector. Now let's talk about what a vector actually is. You might remember from Despicable Me that a vector is a mathematical quantity with both direction and magnitude. The direction is we're going to the right. The magnitude is how far to the right I'm going. So 1, 2, 3, 4, 5. The direction is that we're going to the right, and the magnitude is that we are going 5 units to the right. So what is that going to look like? We're going to do this 2 ways. I'm going to show you, 1, with some tracing paper, and 2, with the applet, because I do want you to be practicing these with the applets. All right, so with our tracing paper first, I'm going to trace this in on my tracing paper. And I am reusing the same tracing paper from another lesson, so it's filled up with lots of stuff, and that's okay. I'm going to poke holes that go through the tracing paper, and the reason I do that is because when I'm moving this and I'm putting it in place, now I know where all of my new points are going to go. I'm just going to do that for just those couple. So I'm moving it so that this point P is now over here at point Q. So I'm going to move that tracing paper until P is at Q. That looks like that's the new position, but how do I get that, which is on my tracing paper, to be on the paper below it? That's where poking those holes comes in handy, because that point is now here. And again, I've poked my hole. There we go. So now I am drawing below the paper. So again, I'm poking through, and now when I color, I'm coloring below the paper. I've poked through, so when I color, I'm coloring below. So you can kind of see I'm putting each of those points in place there. So that's how I'm going to do that. Another way, without tracing paper, because translations are easy to do without tracing paper, you can see, remember our vector, P is going to Q. In other words, we're using that vector to show it's going to the right 5 spaces. So for these other ones that I didn't poke the holes through, I know that this right here is going to go over to the right 5 spaces. 1, 2, 3, 4, 5, and there's going to be a new point there. And this point here is going to go to the right 5 spaces. 1, 2, 3, 4, 5. So we can continue to do that without that tracing paper. In the end, it's going to look like this. And there it is in place, both with and without the tracing paper. Now let's switch back on over. Let's take a look at the applet. So in Canvas, when you scroll down past where you're currently watching the video, you are going to see translate polygon A. So point P goes to point P prime in the image. Let's click on that applet. What we need to do when we're using this applet, we need to first create our vector. So to create a vector, that's going to be this icon here. And that vector tells you, as soon as you click on it, what you need to do. Select the starting point, then the end point. Well, it's starting at P, and it's going to P prime, or Q is what it was on our hard copy. And there's the vector. So now the vector is created. Now I can use this applet to do this transformation. To do the transformation, I click on this. This, you can see, shows the vector, and it shows us sliding something along for a translation. So now I'm going to click on this, and it says translate by vector. So select the object to translate, then the vector. Here's the object I'm translating. Click on it. Now I need to show how much we're translating it. We're translating it by that vector. And okay, let's try that again. Clicking on this. Here's the object I'm translating, and here is the vector that I'm translating it by, and there we go, it's in its new position. So that's how that is going to work on the applet. All right, let's move on to the next problem. This time it's a rotation. We're going to rotate triangle B 90 degrees clockwise using R as the center of rotation, and then we're going to write down the angles when that's in its new position. So let's switch over to the hard copy first so we can do it with our tracing paper. There we go. Gonna trace that image first. Now, one thing as I'm tracing this, one thing I want you to remember is, what does 90 degrees look like when we're on this isometric grid? Remember this isometric grid from a previous lesson. What does that mean? Remember, these are all 60-degree angles. This is 60 degrees, 60, 60, 60, 60. So if I need to get to 90 degrees, that's going to be one 60-degree angle and If I go another 60, that's too much, that's 120. But if I go half of it, that's going to be that 90 degrees. So keep that in mind. Another great way that we can do this is when that's in place. Since this right here is a 90-degree angle, this is going in that direction, and this is going in that direction. So when I rotate 90 degrees clockwise, right? It says clockwise, yeah. When I rotate 90 degrees clockwise, this part right here is going to rotate and become that line. So using R as the center, I'm going to poke a hole through R because that's going to be my pivot point. So poking a hole through R, that's my pivot point. So now when I rotate, that is staying still and everything is rotating or spinning around that. So let me get that back into place. Rotate 90 degrees around R. Remember, this part right here is going to rotate so that it's in place right here. So I'm going to spin it around R. Spinning, spinning, spinning. Now that it's lined up, I know that I've gone that 90 degrees. Okay, and now to make sure I've got it in its new position perfectly, I'm going to poke a hole right here. That's where that vertex is. And then I can put that dot below it, poking a hole right here, dot around it, again poking the hole through, okay? And now I can see where that new triangle is going to be. So this is 90 degrees. Because it's set to label. This is that 60-degree angle. Remember, that 60-degree angle has now rotated into its new position. So this is the 60-degree angle. And this angle was our 30-degree, rotated into position. We can now see that that is our 30-degree angle. There we go. That is how we would do that on tracing paper. And now let's switch on over to our applet. Returning to the applet, this is the same applet as before. That's just for our translation. That's for our last problem. So I'm going to close out of that tab. And now here's our rotate triangle applet. So let's click on that one. Here's how that rotation is going to work. So this time we don't need to do a vector in advance or anything. We don't need to do anything in advance. But I am going to use this tool right here. This tool right here is our rotation tool. So when I click on that rotation tool, it will tell me directions. Rotate around point, select object to rotate and center point, then enter the angle. So I want to do a rotation. This is the object I would like to rotate, so clicking that. And then what is the point I want to rotate around? This is our point to rotate around. And then it pops this up. What exactly are we going to do? It says in the directions that we're rotating 90 degrees clockwise. So I'm going to type in 90. It's set to counterclockwise, so I need to make sure I choose clockwise. Click OK, and it's going to do that rotation for us, just like we saw on our tracing paper. I'm going to close that applet, and now let's do the next problem. Here it says in the image, write the length of each side in grid units next to the side. We might need to do some other tools, but I'm not going to worry about that just right this very second. We are going to be reflecting pentagon C across line L. So it's already set up for us. Here's our pentagon labeled C. Here's our line of reflection. Going straight to tracing paper. Let's see what that's going to look like. Going to get that all traced in there. When I do a reflection with tracing paper, in addition to tracing the object that I'm going to reflect, I also need to trace the line of reflection. Okay, so there's that pentagon traced on my tracing paper. I also need to trace this line of reflection. Because when we do a reflection is a flip. So that means I need to flip my tracing paper, and if I'm going to flip my tracing paper, I need to make sure I'm getting it back into position. When it's a slide, we know it's in position because it's just in the right spot, right where we translate it to. When it's a rotation, we know it's in the right spot because I poke my hole through and I pivot around a certain point. With the line of reflection, when I flip the paper, yes, I flip the paper, but we can tell it's not quite in position. I know it's going to be in position when that line of reflection that I traced matches up with the line of reflection here. Make sure it's not too far up or down, right? It's a direct reflection. So here's the original, which you can see is one step away from the mirror. And so here's the reflection, one step away from the mirror, but on the other side of that mirror line or that line of reflection. So to get it into place, you can kind of see where each of those points are going to be. So I can poke my holes through my tracing paper again. Again, poking that hole through that tracing paper so that then I can place that point underneath, just like that. And you can see where those points are going to be. Now I didn't do it for all of them. So if we don't have tracing paper, what is that line of reflection going to look like? Just like I said, here's the original one step away. Here's the reflection one step away. Here's the original one step away from that mirror line or line of reflection. Our new image is one step away, but on the other side. So this one, here it is all the way over here. Let's count. That's 1, 2, 3 steps away. So where's the reflection going to be? 1, 2, 3 steps away on the other side. This one's going to be a little bit harder. I'm going to go back to my tracing paper to make sure that's in the exact right spot. And same thing here. You can see it's 1, 2, 3 and a half-ish. So it's going to be 1, 2, 3 and a half-ish. I'm going to guess here. But let's go back to that tracing paper and actually see. There's the original. Flip it. Poking it on through. Yeah, looks like my guess was pretty accurate. This one I'm going to put right where it needs to go. And there we go. So now I can draw that figure in place using tracing paper, kind of a combination of tracing paper and without the tracing paper. Okay, what does it look like in the applet? In the applet, again, click on number 3, the applet for that reflection. And here the line is already drawn for us. So if I need to reflect this polygon, I'm going to use this tool. See how it looks like a reflection? That's our reflection tool. Click on that and it's going to tell us we're reflecting around a line or over a line. Select the object to reflect, then the line of reflection. So here is the object I'm going to reflect. Here's the line I'm reflecting it over, and boom, in place just like it should be. And you can see that it looks exactly like what we had using our tracing paper. Okay, now let's come back to the beginning. Now that we've seen in the applet and with our tracing paper what these are supposed to look like, now let's observe some interesting things that we're seeing. It did say that we need to write the length of each side in grid units next to the side. We're going to do that for both the pre-image and the image. Here's this one, it's 2. Now when I look at the image, the new figure, we can see that that same corresponding length is also 2. Here, 1, 2, and we can see here, 1, 2. This has a length of 1, and so we see a length of 1. A length of 3, 1, 2, 3. Corresponding side is 1, 2, and 3. Length here of 2. Corresponding side, 1, 2. 1, 2, 3, 4. And corresponding side in the image, 1, 2, 3, 4. Pre-image, a length of 1. Pre-image, a length of 1, and what do I see in our new or our image? Length of 1 and a length of 1. So that's really interesting. More important than you realize, what we just saw is in a translation, the side lengths stay the same. Nothing changes here. Now let's move on to the next one. And in this next one we can see in that rotation, it says write the measure of each angle in its interior. So I did write those angles down, but I want you to notice that those didn't change either. So that's another interesting point. Let's make sure we write that down. The angle measures stay the same. And it's also important to realize that even though it doesn't mention it here, it's also important to see that our side lengths also stay the same. Let me return to the tracing paper. And here in this tracing paper, notice that this is 2 triangles in length. And even when it's rotated, we can't necessarily measure 2 triangle lengths, but we can see that obviously I didn't retrace that. That's the same traced image from the first time, and we can see that it's the exact same thing here. So I think it's safe to say that even in that rotation, our side lengths didn't change. Just like here, here's our side length. I'm only tracing it the one time when I do that rotation, and it's rotated and retraced into place. I didn't change that length of that line. It stayed the exact same. So the angles are staying the same just as the side lengths are staying the same. So let's write that down as well. Angle measures stay the same and the side lengths all stay the same. Let's move on to that reflection. In that reflection, it says write the lengths in grid units for each of those. So I'm going to do my best to do that. This is difficult because it's not just 2, it's a little bit more. But when I look over here, I can see it's 2 and a little bit more. I can write this one down. This is a length of 3. 1, 2, 3. And the reflection, 1, 2, 3. Some of these are really difficult. This is 2 and a little bit more. This was 2 and a little bit more. So I'm not going to write them down just because they're not going to be precise. But I can see what happened with those angles. Again, let's go back to that tracing paper real quick. In our tracing paper, we can see this is our 90-degree angle. This is 120 degrees. So when I reflect it or flip that tracing paper, I didn't retrace that angle. I didn't redraw anything. There we go. So that angle that was 90 degrees here is now going to be 90 degrees here. And the angle that was 120 degrees, since I'm not redrawing it, is going to be 120 degrees there as well. With that in mind, I think it's safe to relabel each one of these. This is a 90-degree angle. This was 120 degrees. This one is 90 degrees, so when it's reflected, I'm not retracing anything. That is still going to be 90 degrees. 150 degrees, because it's this angle that's then reflected. It looks like 1500. Let me rewrite that. 150 degrees, 90 degrees, and this one here is 90 degrees. So what is happening here? Even in a reflection, in that reflection, we are seeing the same things, that the angle measures are staying the same. And we are seeing that the side lengths also stay the same. We saw that same behavior in each one of these. We saw over here with our transformation, or excuse me, our translation, we saw that the side lengths remain the same. And even though it didn't ask us to, I hope that you observe here, this is a 90-degree angle because it lines up perfectly with those vertical and horizontal lines. And guess what? 90-degree angle lining up perfectly. So we're even seeing the side lengths remain the same and the angle measures remain the same in a translation. Angle measures and side lengths stay the same in a rotation, and angle measures and side lengths stay the same in a reflection. That is pretty important. That is happening because each one of these, and I do want you to write this down, are rigid transformations. Understand this word here. This is rigid. It's not ridged, like ridged or ruffled potato chips. It's rigid. Rigid means unchanging. Someone who is rigid might be set in their ways. So these are transformations. They're changes to these polygons or to these shapes, but even though there's changes, they're ones that are unchanging or staying the same. So what is it that's changing? Rigid transformations are transformations that preserve. Preserve means to keep the same. And what is it that's keeping the same? As we saw, angle measures and side lengths. I'm going to put even distance, side lengths / distance. So we saw that in each one of these. We saw that the side lengths and angle measures stay the same in a reflection. side lengths and angle measured stay the same in a rotation, and side lengths and angle measured stay the same in a translation. So each one of these are what we would call rigid transformations. All right, here's our last activity before we summarize and do our cool down. Here's a grid showing triangle ABC and two other triangles. I'm going to do this one with some technology this time. So I am going to just kind of trace over ABC, kind of mimicking tracing paper here using some technology. All right, and what we're saying is these other triangles, you can use a rigid transformation to take triangle ABC to one of the other triangles. So remember what a rigid transformation is. Something that preserves angle measure and side lengths. So let's take a look and see. I can maybe rotate this around and I can slide it. So I did a rotation and a translation, and I can see, although those angle measures are the same, I can line up each of these angles to be the same. Oh, that one's not it. So that one didn't preserve angle measure. It may have preserved some of the angles, but not all of them. That one definitely doesn't line up. So it's probably not going to be that one. And I can also see that they're definitely not the same lengths, right? That one's my original one that I traced is quite a bit longer. So which one is the one that is the rigid transformation? Let me go all the way back to the original. So I know that it's not EBD, but if I rotate this triangle, and then I can translate it, sliding it into place, then we can see that it does line up perfectly with CFG. So we can use a rigid transformation, meaning rotations, translations, and reflections, and it will get us to CFG. How do I know that that is the one that worked? Well, I know this because triangle CFG has the same angle measures and side lengths. We can see that the other triangle, what was it called? EBD is just too small. It didn't keep the angle measures, it didn't keep the side lengths, so it is too small. I describe a rigid transformation that would work. Well, you kind of saw me do that. We did a rotation and we did a translation. Now, I'm going to add some more detail here because I'm going to go back and talk about some of those things that I mentioned in our applets and in our tracing paper, but I want to make sure that we explicitly state them. Okay, when we are doing a translation, we need a vector to describe it. We need to know the direction and the magnitude. So even if you don't say, here's the vector, you need to be able to describe that it's moving in a certain direction a certain amount. Okay, so the direction and the magnitude. Keep that in mind because when I come back over here and I'm describing that translation, I need to know how much I'm translating it. In a rotation, there are certain things that we need. In order to make that applet work, we needed to know what the center of rotation was. Okay, that center of rotation was this. We also needed to type in how much we were rotating it. So we need to make sure that when we are talking about rotations, when we're defining them, we need to define rotations using a center of rotation. We need to know what is that pivot point. And once we know what the pivot point is, we need to know how much we're rotating. So we need to know the angle and direction of the rotation. A 90-degree clockwise rotation is going to be different than a 90-degree counterclockwise. So angle, 90 degrees, but also the direction, clockwise or counterclockwise. That's how we define that rotation. So again, keep that in mind. As we come back here to this problem and we have to describe how much we rotated it, those are the pieces of information that we need. The center of rotation and the angle and direction. The last one is a line of reflection. Remember in our applet, in order to do the reflection, the applet asked what is the line that we're reflecting over. So when we're doing a reflection, we need a line of reflection. Once we have the line of reflection, we know what we're flipping it over, and we're good to go. So now, with that in mind, we did a rotation and we did a translation. How much exactly did I rotate? Around what point? How much did I translate? I'm going to go back to the beginning. Now, keep in mind, this is presentation software. This is not geometry software. In normal geometry software, I would have to rotate around a specific point. This, everything rotates around the center point. So I'm going to rotate at 90 degrees because we do know it's 90 degrees clockwise. I'm just going to pretend like B was that pivot point, that I poked my tracing paper hole right through here and spun that tracing paper around, and that's where it would end up. So I rotated 90 degrees. I went clockwise. I went in the same direction that the hands on a clock move. And don't forget, we also need the center. So 90 degrees clockwise around point B. And after that, now it's still not in place. Now I need to translate it. So now I need to go, remember on a translation, we need to define the vector, the direction, and the magnitude. I'm going to the right. That wasn't enough. So I need to go to the right, define the magnitude, count how many spaces, 1, 2, 3, 4, 5, 6, 7 to the right. So translation, 7 units. That's our magnitude, and the direction was we went to the right. So keep that in mind as we're talking about these transformations, all of the information that we need to talk about when we're reflecting them. The next one is pretty fun, but I am not going to do it on the recording. It's an Are You Ready for More? And you are more than welcome to try it on your own. But as it's an Are You Ready for More? If you're ready, do it. If you're not ready, don't worry about it. Let's move on to our summary. The transformations we've learned about so far are translations, rotations, reflections, and sequences of these motions. So a translation paired with a rotation, like we just did, or a reflection paired with the translation. All of those are examples of rigid transformations. So we don't need to just call them transformations. They're rigid transformation. Again, a rigid transformation is a move that doesn't change any of the measurements. For example, and you'll remember this, each figure and its image all have corresponding points. So with the rigid transformation, figures have corresponding sides and corresponding angles. And what we're seeing in these rigid transformations, these corresponding parts, whether they're corresponding sides or they're corresponding angles, they have the same measurements. For example, we can see triangle here, EFD, was created by taking triangle ABC and reflecting it across this line here, and then translating it. So that means all of those angle and side measurements stayed the same. They all have the same as the original. In the original, we have this angle is 71.6. So when it's reflected, this angle is going to be 71.6. And when it's then later translated, it still is going to be 71.6. This side length here was 2.24. So when it's reflected, it still is going to be 2.24. So then later on, when it's translated, it's still going to be 2.24. So each of those angles are preserved, each of those side lengths are preserved. Again, corresponding sides have the same lengths, and corresponding angles have the same measures, and that's unique to those rigid transformations, which again are translations, rotations, and reflections, and combinations of each of those. Let's put this all together in a cool down. So trapezoid, A prime, B prime, C prime, D prime is the image of trapezoid ABCD. So ABCD is the pre-image, that's our original. And this is going to be A prime, B prime, C prime, D prime. It's the image after a rigid transformation. Knowing that the points are going to correspond, the angles and the side lengths are going to correspond, we can use that to label these figures. So label the vertices A prime, B prime, C prime, D prime. This right here is A, so that same point corresponding to it is going to be A prime in the new one. Here's B, so I can follow along, that's going to be B prime. This will be C prime, and this will be D prime. And with that in mind, it says label all known side lengths and angle measures. Angle B is 50 degrees, so B prime it's going to be the same, so I'm going to label that to be 50 degrees. A is 130 degrees, so A prime is going to be the same because it's a rigid transformation, 130 degrees. But notice we also have in our new figure, this side length, C prime D prime, is a length of 4. So the original CD is also going to be 4. This A prime D prime is labeled to be 6. So going back to the original, that means AD is going to be 6. That is it for today's lesson. Thank you for watching. Your homework is the Lesson 7 practice problems. We'll see you next time.